Hello students, welcome to Rasaayana. Today I will be taking a very important topic called as valence shell electron pair repulsion theory. Before entering into the theory, we have to understand the importance of VSEPR. For example, in 2024, in the advanced paper, you can see a question related to VSEPR. So how to tackle the geometries of various molecules that are given, and also how many number of lone pairs that are present. All these things we have to discuss, and we will be discussing very smoothly. So let us start with VSEPR. A very important theory. This theory was proposed to explain the geometries of various main group molecules. So molecules related to main group compounds, not the transitional compounds. VSEPR is valence shell electron pair repulsion theory. We also call it as VSEPD. Valence shell electron pair domain theory. It was proposed and developed by different group of scientists. Proposed by Sidwick and Powell. Later it was developed by Gillespie and Nyholm. So much name has come for Gillespie and Nyholm, who have developed this theory. What is the theory based upon? If I want to know the geometry of a given molecule, I should have an idea about the central atom and the atoms surrounding it, or the bonded atoms. So once I am aware of the central atom and the bonded atoms, then I have to consider the valence electrons of the central atom. So how many valence electrons are present and how the bonding pairs are arranged around the central atom, what are the repulsions between them, and how does it lead to geometry? That is all about VSEPR theory, valence shell electron pair repulsion theory. So before entering into theory, let me show you the question that was asked in advanced 2024 paper 1. It was for a 3-mark question. Well, you can go through the question. According to VSEPR model, we have to match list 1 xenon compounds with the corresponding geometry and the number of lone pairs present on it. So you can clearly see that they are not only asking the geometries, but also how many lone pairs are present. When they are asking the geometry, there are two types of geometries. We have to discuss what are those two types of geometries, or different types of geometries. So here they have given xenon XeF2, XeF4, XeO3, XeO3F2. 4 compounds of xenon have been given. 5 options where they have given trigonal bipyramidal with 2 lone pairs, tetrahedral with 1 lone pair, octahedral with 2 lone pairs, again trigonal bipyramidal without lone pair, trigonal bipyramidal with 3 lone pairs. So you can see that there are 3 options with trigonal bipyramidal as a geometry. Options you can see. So before I explain the concept, you may attempt the question. You have to just match the list 1 with that of the list 2. Okay, hope you have taken the question. Now let us understand about this VSEPR and how to arrive at that question. Right. For convenience, to understand about this valence shell electron pair repulsion theory, as I told you, it will give you the geometries of various main group compounds. So let me classify whatever atoms that are present in a given compound. These atoms I am just classifying into 2 types. One I am calling it as central atom. The other I am calling it as a bonded atom or a surrounding atom. Bonded atom or a surrounding atom. This is with respect to the atoms. Now from the basics we are aware that there are two different types of electron pairs in a given compound. What are these pairs? One we call it as a bonding pair of electron, and the other we call non-bonding pair of electron. Or lone pairs. In very few molecules there could be an odd electron, there could be a single electron also, but most of the molecules will have lone pairs. So pairs of electrons I have classified into two types for convenience: bonding pair of electron and non-bonding pair of electron or lone pairs. For a given compound, atoms have been classified into two types. One I am calling it as a central atom, the other one which is bound to that central atom are called as bonded atom or the surrounding atoms. To get the geometry, there are two different types of geometries. These are classified into two. One we call electronic geometry, and the other we call it as molecular geometry. Or simply shape of the molecule. This is for convenience. Atoms classified into two types, electron pairs classified into two types, and geometry also classified into two types. Suppose if I take xenon F2, we have to identify the central atom. The central atom is xenon. The bonded atoms are fluorine. So XeF2, we have xenon as the central atom and fluorine as the bonded atoms. Then how many pairs of electrons, whether they are bonding or non-bonding, and what is the type of geometry? This is what we have to consider. I am keeping this question as such. Now let me take a hypothetical molecule. Just imagine that this is a central atom. To this central atom there are some atoms which are bound. I am calling them as BCD. Just a hypothetical molecule. So here A is called as central atom, B, C, D are called as bonded atoms which are bound to the central atom. Every atom which is present around this central atom, this is bound with a pair of electron. That pair of electron we call it as a bonded pair of electron. So there are two bonded pairs of electrons, three bonded pairs of electrons. But for our VSEPR theory, we have to consider only sigma bonded pair, not the pi. So how many sigma bonded pairs are there between the central atom and the bonded atom? That is what we have to count. Apart from that, are there any other electrons which are existing as lone pairs? Again, that we have to check. So in a hypothetical molecule, here I have given a single bond, a double bond and a triple bond. Single bond is occupying one space. This is the space it is occupying. Double bond is also occupying some space. Triple bond is also occupying some space. So each of them is counted as one space or one domain. So this we refer as steric number. For example, what is the steric number of the central atom A? Then the answer is the steric number is nothing but the number of domains, the number of spaces that are present around the central atom. This is space 1, space 2 and space 3. So altogether there are 3 domains, or the steric number is 3. So the steric number or domains are 3 in number. Okay, maybe I'll take one more molecule. Here there is B, here there is C, and here there is a lone pair of electrons. Here we can see that there is a bond between A and B, 2 bonds between A and C, single bond is occupying one space, double bond is also occupying one space. Apart from these bonded pairs of electrons, we have non-bonding pair of electron which is called as a lone pair. So the lone pair will also occupy some space. It is a localized pair, therefore it will occupy more space. So this is occupying one domain, double bond is occupying one domain, and the single bond is occupying another domain. So in this case, the steric number, which I am abbreviating it as S, or the number of domains, which I am abbreviating it as D, is equal to 3 again. But what is the important difference? The important difference is, in the first case, how many sigma bonds are present? There are 3 sigma bonds and 0 lone pairs. While in this case, steric number is again 3, but there are 2 sigma bonds and 1 lone pair. So though steric number is same, but the number of sigma bond and lone pair combinations are different. So when I look at the geometry, approximately this is looking like a trigonal planar geometry. If I consider the lone pair, this is also looking like a trigonal planar geometry. But what if I don't consider the lone pair? Just as in the case of H2O molecule, whenever we draw H2O, generally we don't draw the lone pairs. Or while drawing the ammonia or nitrogen, we never draw lone pair in general. We draw only nitrogen and hydrogens, or we draw oxygen and only hydrogens for water molecule. That is called as molecular geometry or shape of the molecule. So here, if I ask the electronic geometry, you have to consider all the pairs of electrons that are present around the central atom. There is a non-bonding pair, also there are bonding pairs. Count all of them. And once you count, you will get 3, steric number is 3. Whenever steric number is 3, there is a particular hybridization and a corresponding geometry to that. So that is given by VSEPR theory. Okay, if you have understood this hypothetical molecule, what is steric number? It is a space present around the central atom. How many different spaces are present around the central atom? Whether the space is occupied by a single bond or a double bond or a triple bond or a lone pair, each of them is considered as a space or a domain. Sometimes a single electron, if it is present, single electron also occupies a single domain. Okay. So with respect to this steric number, we have one particular hybridization and a corresponding geometry. Let us understand that. For example, if I give steric number or domain, for steric number 2, 3, 4, 5, 6 and 7. We need not go beyond 7. Beyond 7 also there are few examples which are discussed as exceptions that we'll discuss later. So for steric number 2 to 7, we have different hybridizations. These are sp, sp2, sp3, sp3d, sp3d2 and sp3d3. If you have noticed, there is no dsp2 hybridization here because VSEPR does not consider square plane as a parent geometry. It is coming under a derived geometry, but it is not a parent geometry. So what are the corresponding geometries? For sp hybridization, the geometry will be linear. For sp2, the geometry will be trigonal planar. For sp3, the geometry will be tetrahedral. For sp3d, the geometry will be trigonal bipyramidal. There is no parent square pyramid geometry. Square pyramid is a derived geometry for VSEPR. sp3d2 octahedra and sp3d3 pentagonal bipyramidal. Each of these geometries have different bond angles also corresponding to a geometry. Suppose if I give linear geometry, for linear geometry the bond angles what are the bond angles for linear geometry? We have 180 degree. For trigonal planar, the bond angles will be 120 degree only. For tetrahedral, 109.5 degree or 109 degree 28 minutes. For trigonal bipyramidal, we can have 180 degree angle, 120 degree angle and also 90 degree angle. For octahedra, 180 degree and 90 degree angle. And for pentagonal bipyramidal, we can have 180 degree angle, 90 degree and 72 degree. These are the various bond angles corresponding to a particular geometry which has a particular hybridization along with its steric number or domain. So once if we have understood the different types of geometries, whatever geometry that we have given, all these are called as parent geometries of valence shell electron pair repulsion theory. From these parent geometries, there could be some derived geometries when I consider the pairs of electrons which are bonded as well as non-bonded. For example, trigonal planar. If trigonal planar is a parent geometry with one lone pair, it becomes a bent or angular geometry. Tetrahedra, we have corresponding geometries, trigonal bipyramidal, octahedra and pentagonal bipyramidal. So all these geometries now we have to go through. For example, let me begin with trigonal planar geometry. Electronic geometry, and molecular geometry. For trigonal planar, the steric number is 3. So when I say 3, that 3 could be 3 bonded pairs, 0 lone pair, or it could be 2 bonded pairs, 1 lone pair, or it could be 1 bonded pair, 2 lone pairs. It could be any of these 3. So for any of these 3, suppose if I take 3 plus 0 combination, 3 plus 0 means 3 sigma bonds, 0 lone pair. This is one combination. Or I may take 2 plus 1. It means 2 sigma bonds and 1 lone pair. Or I may consider 1 plus 2, which are very rare, 1 sigma bond and 2 lone pairs. Altogether the steric number has to be 3. Now look at the geometries. 3 plus 0, all are sigma. All are sigma means, suppose if I am taking a molecule, remember axe symbolism. Axe symbolism in VSEPR, AXE, where A represents the central atom, X represents the bonded pair of electrons, E represents the non-bonding pair of electrons. So if I consider the electronic geometry, in this case it will be like A, all are bonded pairs, no lone pair. So the molecular geometry also becomes the same. In both cases the geometry is trigonal planar. I'm just abbreviating it as TP, trigonal planar. In the second case, we have 2 sigma and 1 lone pair. 2 sigma, 2x, there is a lone pair, 1 E is present. It means here I have to write E. In the place of E, I have drawn lone pair. Either you draw lone pair or you put E. Anything is same. Whenever I am drawing molecular geometry, do not consider any lone pair. Whenever I ask you the shape or molecular geometry, do not consider the lone pair. So now if you look at the geometries, this is still looking like trigonal planar, but this is not an equilateral triangle because there is a lone pair. This is not a equilateral triangle, trigonal planar but not an equilateral triangle. In this case, this is bent or angular. Some of you may call it as V shape, but the original terminology is bent or angular. Suppose if I have got 1 sigma, there is only 1 x but 2 e. I am having 1 x and 2 e. It means these are 2 lone pairs. So in the molecular geometry, I should not draw the lone pairs, or e I should not indicate, only x should be indicated. If I indicate only x, then the geometry becomes linear. So this is again trigonal planar but not an equilateral triangle, while this is linear. So these are the various molecular geometries or shapes corresponding to trigonal planar with steric number 3. Steric number is same. Okay. Now likewise, I'll take one more geometry. Suppose if I take tetrahedra, let me take 4 plus 0 combination, 3 plus 1, 2 plus 2 and 1 plus 3. From the axe symbolism, this is 3 plus 1, 2 plus 2 and 1 plus 3. So in all these, the shape or the geometry which is called as an electronic geometry, it is tetrahedra. Bond angles will vary. If I consider the same for the molecular geometry or the shape of a molecule, for the first case there are no lone pairs, so indicate all the bond pairs. Remember, in the molecular geometry you are going to indicate only bond pairs, no lone pairs must be indicated. In the second case, no lone pair indicated, so this becomes trigonal pyramidal. In the third case, no lone pairs, that looks like angular or bent. And in the fourth case, it is linear. You can notice how the electronic geometry is remaining the same, but how molecular geometry can change. So this is for steric number 4, tetrahedra. 4 can have a different combination of 4 plus 0 or 3 plus 1, 2 plus 2 or 1 plus 3 combination. Let me choose the most important geometry, trigonal bipyramidal geometry. Trigonal bipyramidal geometry where the steric number or domains are 5. So this 5 can exist as 5 plus 0, 5 sigma, plus 0 lone pair, or it may exist as 4 plus 1, or it may exist as 3 plus 2, or it may exist as 2 plus 3. 2 bond pairs or 2 sigma, 3 lone pairs, 3 sigma 2 lone pairs, 4 sigma 1 lone pair. Now we'll come to the geometry. When I draw the geometry A, both electronic as well as molecular geometry remains the same. It is trigonal bipyramidal. When there are 4 sigma bonds and 1 lone pair, remember lone pair will occupy more space. So for trigonal bipyramidal geometry, in the equatorial region there is 120-degree angle. Separation is large. So any lone pair or multiple bond will first choose equatorial position. So whatever lone pairs that are present, first of all try to put it in the equatorial position. So here I put 1E. Later on the others are X. Now in this case, put only X. So the electronic geometry still remain the same, trigonal bipyramidal, but this is not looking like trigonal bipyramidal. We have a special name for it. The name is called as seesaw. The other name we give is called as disphenoidal or distorted tetrahedra. 3 different names. Famous one is seesaw. Then we have 3 sigma and 2 lone pairs. So here I put A, 2 lone pairs, don't put any E. This is still looking like trigonal bipyramidal electronic geometry with 2 lone pairs, but if I don't put those 2 lone pairs here, this is looking like a T shape. So the geometry here we refer as T shape. Then we have one more combination, 2 sigma and 3 lone pairs. First lone pair should be given the position of equatorial. These are the bond pairs. Again TBP geometry for electronic, but when it comes to molecular geometry, don't put the lone pairs, put only the bond pairs, then the geometry becomes linear. So how it is varying, you can see in trigonal bipyramidal, electronic geometry is remaining the same with different bond angles. Little bit changes will come because of the presence of lone pairs. But when it comes to the molecular geometry or shape of the molecule, we have TBP with 5-0 combination, 4-1 combination is seesaw, 3-2 combination is T shape, and 2-3 combination is linear. This is with regard to trigonal bipyramidal. Octahedra steric number is 6, and for this 6 steric number, once you know these combinations, then only you can attempt that question, because advanced level questions are not easy to solve, but with clear concept you can very easily solve them. That looks very easy for you. Here we can have 6 plus 0 combination, 5 plus 1 combination, and 4 plus 2 combination. 3 plus 3 combination is unlikely, because when I say 3 plus 3, there are 3 lone pairs which account for 6 electrons and 3 bond pairs, 3 electrons. So that also already become 9 electrons. Main group elements cannot have 9 valence electrons. So we don't take 3 plus 3 combination. We mostly go up to 4 plus 2 lone pairs. So here there are 6 sigma and 0 lone pair, 5 sigma and 1 lone pair, 4 sigma and 2 lone pair. Octahedral geometry A, this is octahedral geometry. Both electronic as well as molecular geometry remains the same. In the case of 5 sigma plus 1, here I am not drawing the lone pair, I am drawing only the bonded pairs. So when I draw only the bonded pairs, now you can check the geometry. It has changed. This geometry we call it as square pyramid. Then 4 plus 2 combination. In 4 plus 2, the lone pair should be given maximum separation. In this case, lone pairs are not drawn. I am drawing only the bond pairs. So it looks like a square planar geometry. In the beginning I told you square planar, square pyramid, these are derived geometries but not the parent geometries for VSEPR theory. So we have 3 combinations for octahedra. 6 plus 0 is purely octahedra in both cases. 5 plus 1 with 5 sigma and 1 lone pair is octahedral geometry of electronic, while molecular geometry is square pyramid. 4 plus 2 combination is octahedra and square planar. This is about the geometries. Now the next part that you should understand is how to get the geometry of a given molecule. To get the geometry of a given molecule, you must have some basics about the valence electrons. And apart from these valence electrons, there is a simple method. From the simple method, I have to count the valence electrons of the central atom. Then I have to assign the bonded atoms. Accordingly, I have to bring or get the steric number. From the steric number, then we can go for the hybridization, electronic geometry and molecular geometry. So these things we will be doing in the next class.